Okay, let's go and get started. Today I'm really just going to go through the book slides for memory just to clean up a bunch of little things that I probably skipped over about memory. And then I'm going to go and do a quick matrix multiply example. You've already experienced this with blocking to show you why caching is so important. And then I will afterwards talk about your project, or I'm sorry, your midterm. Okay?
Sure.
All right, thanks, Matt. I'm glad I got your approval. So memory hierarchy design. Hopefully you at least heard a little bit about it. Matt, what's inside of this design?
It's like the food pyramid.
Except with
the cache on the top.
Yeah, okay.
All the registers.
All right, I removed a bunch of slides because there's only a couple that actually matter. And if I recall correctly, if I try and full screen this, I get a blank screen, which is an amazing feature of LibreOffice.
Are we going to talk about software prefetching?
So maybe. Yeah, that might have been useful for your homework. Well, anyways, hardware prefetching. This is it's done your hardware, and what they do is literally when you fetch some item in a block, you now fetch the next block, or actually the next cache line as well. And with the Pentium 4, y'all remember that processor, right?
Yeah.
Well, you do.
Yeah.
You do? Okay, great.
That's the only one I remember.
Okay.
That specific one.
By implementing this hardware prefetching, they actually got a pretty significant improvement. This is performance speed up. So 1.45 means they got a 45% speed up just by doing this hardware prefetching, which is really, that is a lot. This guy over here almost went twice as fast just by prefetching into the cache. So hopefully you can see that prefetching can be a significant boon. Keep in mind though that nowadays processors are probably doing a lot of hardware prefetching themselves, which may make some of your homeworks a little hard to do.
0.001% increase.
You can do compiler prefetching, where GCC is going to try and insert a special prefetch instruction that they literally added to the ISA to say, hey, prefetch this block of whatever inside the cache so that you could have that data available when you finally need it. So that's before the data, non-fault prefetch doesn't cause exceptions. This actually has to do with the meltdown inspector, which is pretty cool. The idea is that if you're trying to prefetch something, what if you decide to prefetch a piece of data that's outside of your process's memory space?
We don't care.
Why don't you care?
You're not hopefully going to be accessing it anyway.
Right. So in general, we don't care because we won't have accessed it. But keep in mind that even though we've requested a piece of memory that's outside of the cache or outside of our process space, it is sitting inside the cache. It's just as long as we don't try and access it, we won't have any errors. Meltdown Inspector actually going to take advantage of this feature, but we'll get to that.
Feature.
Feature. But we'll get to that later. All right, register prefetch. It goes ahead and loads data straight into the register before you need it. All right, great. And cache prefetch, which is really what we care about most of the time, is preload data in the cache. And then loop unrolling and software pipelining. The idea is that you usually have a for loop for I equals 0 to 100, blah, 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 blah. Maybe instead you have a for loop that's from I to 25, and then you have 4 iterations of your loop inside of it. So you don't have to be branching as much. And then the compiler can try and optimize more by prefetching certain loads and doing more computations in parallel.
Sounds like a homework question I didn't do.
Summary. Oh wow, there is no way to read that.
Small and simple caches.
All right, trivial, widely used. That's great. Way predicting caches. All right, the Pentium 4 used it. Wow. Pipeline cache access, of course, widely used. Non-blocking caches, also widely used. What that means is that you can have multiple loads and reads basically out as well. So if you need to load a bunch of stuff, you can send those loads out. You don't have to wait for one load to complete before you start the next load. Banked caches, that's usually to more of a performance improvement. Which bank is it in? It's like caching the cache. I guess it's the best way to do it. Protocol. Okay, so there's a bunch of different technologies that are in use, and wow, we cannot read this at all. We'll go on. So another thing I didn't quite talk about is memory technology. Has changed quite a bit from standard flip-flops to what we have today. Namely, with memory or with caches, it's all about latency. How quickly can you service the request? With memory, it starts to go a little more in bandwidth, because usually when you go to main memory nowadays, you're asking for a big chunk of memory, and you want to take that big chunk and put it into an entire cache line. So it's really more about your bandwidth. How much can you move per a transaction? Yeah, and so now DRAM is used for main memory and SRAM is used for cache. Hopefully we talked about those two. SRAM, okay, requires low power to retain a bit, but it ends up requiring about 6 transistors per bit, which is actually very high. So in other words, it's going to require a lot of area to implement your SRAM. And what that comes down into, well, one, you can only put so much RAM in there because it's SRAM, but also that means you're going to have certain performance issues if you have too much SRAM, because that's a really wide area that your flow of electricity must go through. DRAM works a little differently. Do they talk about how it does? Okay, so DRAM is basically a capacitor that can hold its value for a certain amount of time, and then once that capacitor discharges, you need to refresh it. You need to basically guarantee to refresh it or recharge it, so to speak. I'm using very loose terms here because we're not electrical engineers. But you have to rewrite to it or refresh it so that it doesn't lose what it remembers. Usually, what does it say, 8 milliseconds? But keep in mind that that means every 8 milliseconds you can't do anything with DRAM. You have to wait for it to refresh.
Terrible.
Yeah, well, yes, but now you have only 1 transistor per bit, which is a whole lot better. And you can do multiplex the address lines, which means you can go the row and column at the same time to access a piece of memory, kind of. It allows us slightly faster lookups.
Can you go back a second? Now you said because it has to be refreshed, you can't access it
During the refresh, you can't do anything. So it's literally stalled, so to speak, every
Is that the reason memory is?
one of many.
Okay.
Also accessing it, while you can usually get a lot of accesses going at once, it's still slower than SRAM as well. But the benefit of it is you only need 1 transistor per bit, so you have higher capacity, but slower access. You know, big is slow, small is fast. All right, keep in mind Amdahl's law. Hopefully I've been harping on this, probably haven't been as much. Amdahl's law is always attack the slowest piece until it's no longer the slowest.
And then attack the next slowest.
And then go there, right. Always attack the bottleneck. But same thing here, ends up being that memory capacity should grow linearly with processor speed. Unfortunately, memory capacity and speed has not kept up with processors, kind of, sort of. I would say recently this has not been the case. They've been pretty steady. Let's see. You can try and do multiple accesses in the same row, which happens. Synchronous DRAM, add a clock to DRAM interface. Yeah, well, the big thing here is actually burst mode, where once you get the first word, it's going to give you the rest of it as well, because you're probably going to need that soon. Wider interface, double data rate, and then multiple banks. All right.
So when you have like DDR4, what does that mean?
I'm glad you asked that. So right back in 1980, we just had something called DRAM. What was it? Slowest DRAM took nanoseconds, fastest 150 nanoseconds to access. And what do we got? Cycle time, that means the time you had to refresh. 250 nanoseconds. Well, that's actually not that bad. Chip size 64 kilobits. Not too good. But notice that you go from DRAM to SDRAM, DDR, DDR1, DDR2, DDR3.
That's revolution.
Yeah, that's when I first saw that. I was like, oh, we're gonna be doing a little dancing here. All right. It gets faster, and yeah, it just gets faster, and you can hold more. Is really what it comes down to. Wow, they're going. All right, hold on. Before that, let me answer your question. There we go. So DDR2, the big optimization there was lower power and then a higher clock rate. DDR3 went back to 1.5 volts, but got even better clock rate. DDR4, I'm just reading the slide. Again, lowering the voltage, higher clock rate. Really, they've been going with trying to get the voltage as low as possible to produce the least amount of heat so that they can increase the clock rate as well as how much can be sent through.
The absence of cold.
The app, yes. Right. There is no cold. And then a lot of your graphics memory is actually based off of regular DDR. Okay. Yeah, most of the time with graphics, they just widen the bus so that it can spit more out at a time. And that's really, and you can have a higher clock rate because you don't have to put socket RAMs in. It's directly soldered onto the board. So there's a couple more advantages to that. And that's really what it comes down to with graphics memory versus main memory. Besides that, they function basically the same. Another thing to reduce power is, yeah, they keep lowering the voltage, but they usually also have a low power mode, where if you're not using it or you're not using a bank of it, because when we talk about banks, it's going to have different portions of memory, and you can turn off your different banks or put them in low power mode until they're used. Hey, good, we have a graph. I love graphs. So in low power mode, it must take, for example, in this one, 100 milliwatts. Then maybe typical usage, about 300, fully active, up to about 500. But the idea here is that by adding a power mode to each bank, you can turn off certain banks to consume reduce power, which is really important for your phone. You got that, Matt? All right. All right, if I do stop me, you notice I'm kind of jumping around a lot, and that's because I'm just trying to fill in all the holes I didn't get to in the other slides.
You're thinking.
What? You're thinking?
Thinking.
Good. All right, flash memory. I love the acronym. Always cracks me up. I think it's electronic erasable programming read-only memory.
I thought it was ROM.
Yeah, it should be EEPROM. But think about that. It's read-only memory, but it's electronically erasable and programmable. I think there's a contradiction here. I don't think you're saying what you mean to be saying. But the idea is that once it's kind of flashed, I always think of it as burned in, but flashed, it is read-only until you're able to erase it again. But the point here is it has to be erased before being overwritten. So there's a third operation. Usually with memory, you just write or read. Now you must, if you're going to write to it, you must first erase it and then write to it. But it is luckily non-volatile. It usually has a limited number of write cycles. It's cheaper than SD-RAM, but more expensive than disk. Again, slower than SRAM, but again, faster than disk. And by disk in this case, I'm talking about your standard spinning disk hard drive, because SSDs are basically this nowadays, which is what we use most of the time. If we could just get an updated version of these slides.
Unless you're into chemistry.
Yeah, then you just
You
do.
don't see very many EEPROMs in computers, though.
Well,
In your typical,
okay, EEPROM. You see very many regular EEPROMs. All flash memory is a EEPROM. EEPROM is kind of an umbrella term. So your SSDs are in a way an EEPROM, but we don't call them that. But yeah, you are correct. The old regular EEPROMs you don't see very much anymore. Oh, this was always my funniest. So you got
I
to.
never thought of it like that, but the SSDs are a type of EEPROM.
Yes, because you have to erase before you can write, and then they hold it. And you can only have a number of cycles. Yeah, they're a type of EEPROM. They've just been highly optimized.
Like that.
Yeah, yeah. The technology's come a long way.
I mean, back when I started working for the Navy, we had these huge
Oh, yeah.
EPROMs, that you burn, send out to the ship for them to,
Yep.
every time there was an upgrade.
Oh, I believe you. Yep. Yep. It's just a solid state drive. All right. I always love this comment. Memory is susceptible to cosmic rays.
Thanks, Thanos.
Yeah, that's what I think. I think of like some superhero throwing cosmic rays at my hard drive. Oh no! Or my memory. Ah! Okay, but yeah, it is true. Radiation can mess it up. But they usually are shielded. Soft errors. You probably have seen ECC, error correcting code, memory. There are some, things happen, right? And if it's ECC, they'll try and do some error correction to confirm or actually recover from the error and give you an exact code. On the other hand, if it's a permanent error, then your memory has to start either having spare rows to replace the defective rows, or just the whole thing goes down.
Oh, so this is about the rows themselves actually just being completely unusable?
Mm-hmm.
Okay.
So ECC, that's all done in the hardware.
Yes,
Is that,
at least when up here, what we're talking about, yeah. You can try and do it in software, but that would be way too slow.
I mean, when you buy a ECC memory chip, it's all kind of.
Yeah, it's all
in there.
it's all built in. You're really just paying more money for being able to automatically recover if there's an error. But as long as it's not a sensitive device, I guess, then regular memory is going to be just fine. All right. I forgot what chip kill was about.
Parodies, man.
Parodies, yeah. All right, virtual memory. Actually, did we talk about virtual memory?
I think so.
Yes, we did with the TLB. Good. We can skip this. Each process has their own memory space. Everyone, does that sound familiar?
Sure.
Mm-hmm.
Okay, great.
TLB hits. Yep.
Virtual machines is going to be something different. Virtual memory is how the operating system shields every process. Virtual machines is something in the ISA that supports running different super user modes, so to speak, or different kernels. And you can share a computer among, many unrelated users. Usually, in old virtual machines, there was no hardware support, so it was a very slow operation. Now you actually have instructions in your ISA so that you can create a hypervisor and be able to run different machines at the same time. Allocate this memory for this machine, this memory for that machine, and then sandbox them out so that the different super users or privilege modes can't interact with one another. This is y'all probably are used to this since y'all have been using VMs a lot.
Sure.
No? All right. Of course, in a virtual machine, every virtual machine is going to maintain its own virtual memory inside of it. And so that adds another layer of memory between physical and virtual memory called the real memory, right? Really, the point here is that just keep in mind that you have your virtual machine, which is a full separate sandbox, and then the operating system in each virtual machine will have its own virtual memory system to sandbox the processes inside of it. All right. That's really what's important right here. Is that it? Oh, we're done with that slide. Any questions? That's our tour of memory. Okay, great.